Today we're going to talk about the ideal gas law. We're going to talk about where the ideal gas law comes from, what it means. We're going to talk about R, which is the gas constant. You have to be able to pick the correct units for R, and then we're going to go over how to solve an ideal gas law problem. It's basically an algebraic equation, and you solve for the unknown variable. Before we do that, we want to talk about a couple things. If two quantities are directly proportional, that means that as one increases, the other increases, or when one decreases, the other decreases. So if x and y are directly proportional, then if we write an algebraic equation for those two, then x equals ky, where k is a constant. So if they're directly proportional, then they will be on opposite sides of the equal sign. So why do they need to be on opposite sides? Well, if you just look at the equation, if this is constant, if x goes up, then for k to stay the same, y also has to go up. Or if y goes down, for this to still be equal to x, x has to go down. That's what directly proportional means. One goes up, the other goes up, one goes down, the other goes down. If they're inversely proportional, then that means as one increases, the other decreases. So if we look at x and y again, if x and y are inversely proportional, then xy equals k. Remember, k again is our constant. So if they're inversely proportional, they're on the same side of the equation. So why are they on the same side? Well, if x goes up, in order for that to still be equal to k, y has to go down. Or if y goes up, x has to go down to equal this constant. That's what direct and inversely proportional mean. Now that's important because if we look at how an ideal gas behaves, this is going to help us come up with our ideal gas law. So, if you were to reduce the external pressure of a gas by putting a balloon in a vacuum, and that's a flexible container, remember, if you reduce the external pressure of a gas, then the volume's going to increase. And as the volume of the balloon gets bigger, what's going to happen to pressure? Pressure is going to go down. So this is an inverse relationship. They are inversely proportional. So pressure and volume need to be on the same side of the equal sign. If you put a balloon in the freezer, temperature is going to go down. What's going to happen to the volume? Well, when temperature goes down, kinetic energy goes down. You get less collisions with less force, so volume is going to go down. So that is directly proportional. So volume and temperature have to be on opposite sides of the equal sign. If you put more moles of air into a balloon, you blow into a balloon, what's going to happen to the volume? Well, the volume goes up because as you increase the number of particles, you increase the number of collisions, pressure goes up, that causes volume to expand. So moles and volume are directly proportional. And if they're directly proportional, they have to go on opposite sides of the equal sign. So if we take all of that into account, if we want to satisfy all those requirements, then we end up with pressure times volume is proportional to moles times temperature. Pressure and volume have to be on the same side, moles and temperature have to be on the same side, and then pressure and volume are opposite of moles and temperature. Now, what relates these two sides to each other is called the gas constant, and it has the letter R. And here's our gas law. PV equals nRT. PivNert is an easy way to remember it. So P is pressure, V is volume, N is number of moles, R is the gas constant, and T is temperature. Temperature has to be in Kelvin, and volume has to be in liters. So there are a lot of different values for R because there are a lot of different units for pressure. Most of our problems we'll try to do like atmospheres and millimeters of mercury. So to figure out which R you need to use, you need to look at your problem. If the pressure is in atmospheres, then you should use this first value for R, 0.0821. There's atmospheres. If it's in millimeters of mercury, you use 62.36. If it's in kilopascals, you use 8.31, and you see since torr is roughly equal or equal to millimeters of mercury, those two constants are the same. So to pick your R, you have to know what the units for pressure are. If you're solving a problem for pressure, then the R that you pick will tell you the units for that. So if you're solving for pressure and you want pressure in atmospheres, you should use 0.0821. Also, if you notice, in all these R's, volume is in liters. So volume has to be in liters for the ideal gas law. And if you look, all the temperatures are in Kelvin. So temperature has to be in Kelvin. So let's look at a sample problem. A 3.5 mole sample of an ideal gas has a pressure of 1.2 atmospheres at 35 degrees Celsius. What is its volume? So first thing we should do is let's set up the variables. Let's figure out what we know. So we have pressure and volume on one side of the equal sign. We have moles, R, and temperature on the other side. So let's set it up like this. So we look at the problem. We know the pressure is 1.2 atmospheres. Do we know the volume? No, the volume is what we're trying to solve for. The number of moles is 3.5. And then for R, since pressure is in atmospheres, we use 0.0821. Temperature is 35 degrees Celsius. That's got to be in Kelvin, so 35 plus 273 is 308 Kelvin. Alright, so here's all our variables. Here's our equation. So let's plug everything into our equation. And we need to solve this for volume. So let's multiply this side together first. Doesn't really matter how you do it as long as you can solve it correctly. So we got 1.20V equals 3.5 times 0.0821 times 308. That's 88.50. Divide both sides by 1.2. And we get a volume of, let's round it off to 74. We'll do more about rounding later. And then, since it's volume, the units have to be liters. And there's our example problem. So all these problems will be the same as this, except you may not be solving for volume. You might be solving for temperature, you could be solving for pressure, you could be solving for moles.